as I told you, it's clearly written in the book that I is not I dot I. This is not unit vector, this is called unit dyad. It means like a vector has three directions, I, J and K. I'm not talking about n-dimensional vector, I'm talking about just three-dimensional vector. If a vector has three components, some A, I, B, J, C, K. Similarly, a dyad has 9 components. And these are the components and these are the kind of direction. I means this. IJ means two direction like this.
So why, like, how can you differentiate between the two? Like, if you're not saying that, is there some operator or something like you want to put between U and V to differentiate and say, okay, this is the tensor representation of UV, not the scalar? Or they just...
Can you say again once?
To me, when I look at UV like this, I just think of the dot product.
Okay, I have a question.
Like how...
I have a question.
This is just you write next to it dyad or something.
This is representations which is I read in the book.
Okay.
So first of all, if I ask, my quantity is in this direction. Okay, 2. What you will say? Is it a vector?
No.
Or it's little bit higher than a vector, that is a tensor.
I understand that. I'm with you 100%.
Okay.
Just the representation is just...
But the thing is, if there is a dot, then you will say it's a scalar.
So you just, there's no dot?
There is no dot.
Then we understand the
Yeah.
this.
That's why I'm saying, this is triad, which has 3 directions.
Okay.
And it has 27 components.
Okay, no, I have no problem with all of that. I'm just like looking at the representation.
I'm trying to discuss the things, what concept I understood. If you will discuss with me, I think I will try to rectify my concepts. If you have a better idea, just tell me. Because even I am very new to this subject. Dr. Jain.
The magnitude of the dyad, how can you define that?
What I think, because like for a dyad, this is dyad presentation, so its magnitude will be norm of the matrices.
So it will be the Taylor modulus law for Venus law. So I mean like just the square of all the coefficients.
Yes.
Or will it be the matrix law or
honestly, I didn't see its magnitude anywhere, but I think because it said, like if you have a vector is represented by this array, AI cap, BJ cap, CK cap. So its magnitude is the norm of this one. And they said the we can represent a dyad or a triad into m into n matrices. So I think its norm will be the magnitude of that one.
When we use the dyad,
So it's not like you're getting the for example, if you have two vectors, as you're saying, is that representing it in a tensor. So the magnitude of that tensor is not, or is it the magnitude of each vector added together?
It was not written.
According to this, it's probably not.
Yeah, that's for sure. Because the magnitude of dyad should be, because when they are representing a dyad in matrices format, it means its magnitude will be the norm of this one.
Actually, I would guess more it would be the matrix law itself. What you describe is actually called the Venus law, and the matrix law will be like how much you magnify or unify the maximum. Because yeah, of course I didn't read any of this, so I'm just guessing.
Okay, but the thing is that I will note down this question that how to find out the magnitude.
Or
Because
like,
even I am not very
that,
sure about this one. This is my guess.
Or do they define that? Because like one thing is interesting that, for example, you have matrix completion. This one is like the dyad is basically just a matrix. So in the sense that if you want to have the low rank matrix, then it's like the kind of like minimize the long here. That would be a matrix long. Actually, they use for Venus law or they use
nuclear norm minimization.
Yeah, they have the nuclear norm, right? So if we extend that even in higher dimension, let's say just one more dimension, right, higher, then it's something like we'll be able to represent some other stuff. Then maybe we need to do something similar also like to know what kind of law they use and stuff like that. That law will become similar to the magnitude law. That's why.
Okay, I will check on this one.
Okay.
But still,
No,
this
no,
was
no,
just my
no,
idea
no,
because
no,
I
yeah.
didn't find anywhere. I have to Google it. What's the magnitude of a tensor? Now, this was a good question. I was trying to explain you that is every scalar is tensor zero? Actually, tensors. When we talk about tensors, then tensor is mainly used by Einstein for the theory of relativity. If you have the basic idea of theory of relativity, it has multi-frames. One frame is stationary, another is moving, and they try to measure a quantity in two different frames. Are you aware of Einstein's theory of relativity? A basic.
Yeah.
Means according to theory of relativity, suppose I am standing and I am measuring this length. Say this is 1 meter, and suppose there is another guy who is moving in a bus or a very speedily. If he tries to measure the same length, but he is in a different reference frame, so he will measure a different length. So the thing is that all scalars are tensor. No, this is not true. According to theory, if you measure a quantity and if it is independent of the reference frame, then it is then the scalar will be tensor zero. Okay. For example, temperature. I am measuring a temperature. I measured say 35 degrees Celsius, and another person who is moving with the speed of light or compared to speed of light, if he measures the temperature of the same point, he will measure the same reading. So temperature is scalar, but it is tensor zero. But suppose I am measuring a length, and another guy who is moving, he is also. Oh, sorry, I am not talking. It's a scalar. I am talking about time. You know, suppose there is a time interval of say 10 seconds. I am measuring that these two events occur after 10 seconds, and somebody who is moving very fast compared to the speed of light, and if he measures the two events, the time will be little bit more. Okay, so the time will be not same. So time is scalar, but it is not tensor zero. You got my point? With the change of reference, like I am a stationary reference and somebody who is moving, that is a moving reference. For him, the time interval will be not same for the same events. So this is not considered as tensor zero. The same thing as with the vectors. All vectors, all tensor of rank 1 are vectors. But all vectors are not tensors. For example, displacement. If I talk or displacement, or you can say position vector. Say this is a point P. Its position vector will be this. If I change the reference, do you think the vector remains same? Do you think position vector remains same? No. So position vector is not a tensor.
So I'm thinking, why should we consider the reference into the tensor?
Actually, tensors are basically used with the reference